All right. There we go. Okay. Boop, boop. Okay. All right. So we're trying to show that the set of all vectors of the form where their first and last um, elements or entries or components are equal to 0. And we want to show that this is a subspace of R4. Okay. So according to the definition, we need to show two things. We need to show that V1 plus V2 is in S. Okay, and then we also want to show that the scalar multiplication, so C times V1 is in S. So to show that it's a subspace, okay, so S is the set of all vectors of this form. Okay, all right, so let's show each of these, and if the subset, if S is closed under vector addition and scalar multiplication, then it's a subspace of R4. So here we go. So V1 plus V2 is 0, A1, A2, 0 plus 0, B1, B2, 0. Adding component wise, you get 0 plus 0, you get A1 plus B1, you get A2 plus B2, and you get 0. Okay. If we call A1 plus B1 and A2 plus B2, let's say a different element, let's call it C1 and C2, 0. Okay, then this is definitely in S. It has the same form as S, since the addition of two numbers produces an output of a single number. Okay, so it is in it is closed under addition. Let's see if it's closed under scalar multiplication. So C times V1. This is not a dot. That's just multiplication equals C times 0, A1, A2, 0, which is equal to 0, C times 0 is 0, CA1, CA2, and 0. And again, if we relabel these as, let's say, 0, K1, and K2, and 0, okay, then this is definitely within S, where K1 is equal to C times A1, since the product of two real numbers is another real number. Then this is in fact still in S, and so that shows that the vectors of this form under these operations, they're both closed, is a subspace of R4. Okay. All right, let's try another example. So in this next example, we're looking at A is an M by N matrix, so it's something of the form like that. Okay, so it's an M by N matrix. Show that the set S of all solutions of the homogeneous linear system. Okay, so AX equals B is a subspace of Rn. Okay, so we want to show that this is true. So to do that, again, we're going to have to show that the closure under addition and also scalar multiplication holds. Okay, so let's define, let's say x1 equal to a solution of AX equals B. Okay. Specifically, since it's the homogeneous situation, okay, that means that B is identically equal to 0. So we have AX1 equals the 0 vector. That's what it means to be in the set S. Okay, and then let's look at A2. If it's in the set, then that also implies that this is identically equal to 0, since it's the homogeneous situation. All right, and so if we compare this, that means that AX2 is simultaneously equal to 0. Okay. All right, so if we look at V1 plus V2, well, this is by V1, we mean X1 plus X2. Okay. Where these are going to be formed from the multiplication of multiplying this by A. Okay. So we have AX1 plus AX2. Okay. And since the matrix multiplication is distributive, we can write this as AX1 plus AX2. Since each of these individually are equal to 0, and that's what it means to be in this set. Okay, we have 0 plus 0, okay, which indeed shows then that A V1 plus V2 is in S. Okay, so it is definitely closed under this vector addition. Okay, and then we want to look at A C V1. Okay. Well, CV1 is a CX1, so we're going to compare that. Okay, and so scalar multiplication, as we know, is you can factor it out of the order, and so using the fact that, well, I can technically what I'm doing is this, but this is associative and commutative because the constant, it's multiplying it into each of the elements C and then factoring it back out. So this is actually equal to CAX1, where I've used the associative property here and the commutative property here. Okay. The matrix multiplication is commutative with respect to the scalar multiplication. Okay, but AX1 we know is C times the 0 vector, which is 0. So this is still in S. Okay, and so that checks that the set of solutions to the homogeneous equation AX equals 0 is a subspace of Rn. Okay, all right, I think there is one or two more. Yeah, let's see. Next problem, or example, I guess, not problem, example. Show that the set of M vectors whose first component is 2 does not form a subspace. All right. Okay. So we're going to let V1 equal. Let's do this set of M vectors whose first component is 2. Okay, so the 2 is not 4. And then, okay, so we'll have A1, B1, and C1. Okay, so that's our first vector. And then let's consider our second vector. It'll be the same form. So 2 A2, B2, C2. Okay. All right, so let's compare then these two vectors. So let's consider V1 plus V2. Okay, so if we add these two together, we have 2 A1, A2, sorry, B2, C2, C2. Getting ahead of myself. Plus 2 A2, B2, C2. Okay, adding component wise, we get that this is 4 A1 plus A2, B1 plus B2, C1 plus C2. Okay. But look here. This is not the same form as these, and there's nothing I can do to this 4 to make it into the same form. So this is not an element of S. In other words, this is not closed under this vector addition, and therefore this is not a subspace of Rm. Okay. All right, and then in the next one, let's see, it says show that the set of all solutions of A, X equals B, where B is not equal to the 0, does not form a subspace of Rn, where it's not a subspace of Rn, where A is an M by N matrix. Okay, so let's call it X1 equal a solution to AX equals B. That is kind of like in the last one, right? AX1 equals B1. Okay, where B1 is not, not B1. AX1 equals B, which is not equal to 0. So this is not the 0 vector. Okay, and then we'll do the same thing for X2. So this is the system that we're trying to solve, which implies then that AX2 is equal to B as well. Okay. So just like before, we want to show that this is true, where we say this is X1 and X2. Okay, we're hoping that this is still in the set. So using the distributive property, we have AX1 plus AX2. Using the distributive property there. Okay, but this is equal to B plus B, which gives us 2 times B, which is not equal to B. Okay, so since that's no longer in the set S, which is not in the set S, okay, so that tells me then that this operation is not closed under this vector addition. So this is not a subset of the Rn as shown. Okay, so there are 2 examples where it can fail for closure reasons. Now, both of these happen to do with the addition. If you check the multiplication, you'll find that that's also true in this situation. Okay, all right, I hope that was helpful, and I'll see you in the next video.